All right, so let's go ahead and work another DTFS example. This one is still going to look at a sinusoid, but instead of doing the inspection method like we did in the previous video for this example, we're going to work it using the definition of the DTFS coefficients that we derived and actually plug directly into that equation to evaluate and solve for the DRs that we need. All right, so DTFS of a sinusoid using kind of the definition of the DTFS coefficients. We are going to find those coefficients for the particular case of x of k equals sine of 0.1 pi k. So the exact same sinusoid, only difference being the previous example, we just had omega naught k. Now I've actually chosen a specific value for omega naught, but still essentially the same problem. One thing we might ask ourselves initially is x of k actually periodic or not? Well, we know how to check for that. Not all discrete time sinusoids are periodic, but if its frequency over 2 pi is a rational number, then we know that the sinusoid is indeed periodic. So let's go ahead and compute the ratio of omega over 2 pi. In this case, the frequency is 0.1 pi, so I have 0.1 pi over 2 pi. The pi's cancel, and I have 0.1 over 2, which is the same as 1/20th, which is indeed a rational number. So this is a periodic signal. And we have another equation that we can use to actually solve for the period of a discrete time sinusoid. If you remember this equation from earlier, I can solve for n naught by finding the smallest m such that this quantity turns into an integer. So we plug into this our value for 2 pi over omega, which was 1 over 1/20th, which is just 20. And then we find the smallest m, which is an integer, such that this product is an integer. Well, in this case, it's almost trivial, because when m is 1 times 20 is obviously 20, which is an integer. So pretty easy to solve for in this case, and we can figure out that this sinusoid that we're dealing with is periodic with period 20, which means its fundamental frequency is 2 pi over 20. So we now know its fundamental frequency and its period. So that means it is reasonable to try to write x of k in this DTFS representation, a summation of weights times complex exponentials that are all multiples of, and that's important here, I need that multiples of the fundamental frequency. One of the big questions that we always have when doing the DTFS is I know I need to sum over n consecutive values, or n naught consecutive values, but where I do that summation is up to me. So that's one of the choices you always have when working a DTFS problem, is kind of choosing the best set of values to sum over. For this particular value, we're going to go ahead and sum from minus 10 to 9. That is indeed 20 total samples, right? 9 minus a negative 10 plus 1 gives me 20. So this does indeed include a 20 terms in the summation, so it's 20 consecutive values. You might try something else. You might try summing from 0 to 19. That'd be fine. Or you might want to sum from 1 to 20. We'll see, I think, why this works out well for this particular example here in just a minute. So this now is what I need to evaluate. I need to be able to plug in the DRs into this representation if I could just compute the DRs. So let's go ahead and work on computing the DRs from the definition, which is 1 over n naught, the sum over 20 things, again I'm going to go from minus 10 to 9, of my signal projected onto exponential of the fundamental frequency, multiples of it. So that's kind of how I remember and think about the DTFS. So how am I going to evaluate this equation right here? So as a first step, let's go ahead and rewrite the sign in terms of a difference of complex exponentials, right? I can think of sine of x as e to the jx minus e to the minus jx divided by 2j. So that's just me writing down sine, and then I need to leave this part there, obviously. So let's do that, and then I'm out of room, and we just rewrite what we had down right here. And then let's start working on this just a little bit. Let's go ahead and bring the 1 over 2j out front. So 1 over 20 times 1 over 2j is 1 over 40j. And then the summation stays the same. And then let me go ahead and multiply this through on each of those. Let's just do the distributive rule. And you'll note that these have some very common terms. They all have a j, they all have a 0.1 pi, they all have a k. The only difference is this one doesn't have an r, and this one does. So I can factor out all the common terms and write that as 1 minus r. And I can do a very similar thing on this next one. I can distribute this times this, factor out all the common terms, and I end up with 1 plus r on that one. All right, so that's what I end up with. And then one more little step here. Instead of writing this as a sum of differences, let's write this as a difference of sums. Remember, this is just me adding up a whole bunch of things. And what am I adding up? I'm adding up a whole bunch of things that are being subtracted from each other. So an equivalent way of writing that is a sum minus the other part of the sum. I'm kind of distributing that summation to each of these parts. All right? So if we're okay with that, now we're doing real well, because I look at this and I recognize what this is. We've seen this summation before. If you recall that when we have summations of this form, most of the time we get 0. In fact, this summation is 0 unless r is equal to 1. Similarly, this summation is 0 unless r is equal to -1. Where is that coming from? We'll go back in this playlist and watch a video, and we solve for the fact that this summation is equal to 0 when r is not equal to m, and this summation turns into n naught for the case when r equals m. And that's the exact same form that I have here. So now this is pretty easy to evaluate. So again, what am I evaluating? I'm trying to solve for the drs, which means I would like to know, d of minus 10, d of minus 9, d of minus 8, all the way up to d of 9. And now that's pretty easy to figure out. When r is -10, this is 0, and this is 0, because those terms are 0 unless r is 1, or unless r is -1. -10 is neither of those, so I get 0. Same thing for minus 9. Same thing for minus 8, all the way up until I get to minus 2, and that's the last non-zero value that I get. The next value that I get something interesting is when r is -1. When r is -1, this is 0, but this one is non-zero, and in fact this turns into n naught, which is 20. So I'm going to get 20 over 40j, and then there's a minus sign right there that I need to account for. So minus 20 over 40j, 20 over 40 is a half, so I end up with minus 1 over 2j. Multiply numerator and denominator by j, you'll get another negative sign, and you'll end up with j over 2, and j is just e to the j pi over 2. So I end up with this number right here for d of minus 1. All right, you can keep going. D of 0, I get 0. D of 1 is where my next interesting value occurs. This is when r equals 1. When r equals 1, this is 0, but this is non-zero. What do I get? I get 20 over 40j, right? Because this turns into just n naught, just like our rule up here says that it does. 20 over 40j is 1 over 2j. Multiply top and bottom by j again. I get minus j over 2, which is equal to 1/2 e to the j pi over 2. I'm sorry, e to the minus j pi over 2. Negative j is down 90 degrees, so e to the minus j pi over 2. All right. And just for completeness, we can go ahead and list the rest of these, D2, D3, D9. As we go down the list, these are always 0, so we just get 0 for all those remaining terms. All right, what do these look like? So we found out that the DTFS coefficients for the sinusoid were all 0, except for 2 of them, just like we did in the previous video, so nothing too surprising there. Let's go ahead and plot them. So I went ahead and plotted the original discrete time sinusoid itself in the time domain. So this is the periodic signal that repeats every 20 samples. That's it just going along in time. Remember, our DTFS coefficients in general are complex, and they were for this particular example. So when we plot them, we're going to plot 2 quantities. One quantity is going to be the amplitude spectrum. One quantity is going to be the phase spectrum. So let's talk about the amplitude spectrum first, which I plotted right here. When we plot it as a function of frequency in increments of the fundamental frequency. So I have 0 times the fundamental frequency is that little piece there. Then 1 times the fundamental is right there, and 2, 3, 4, 5, all the way down, okay? So this piece right here is at the fundamental frequency, 1 times it, and this is at minus 1 times it. Both of our DTFS coefficients at those frequencies had magnitude 1/2, so we see 1/2 there. And then we see these numbers repeat periodically up and down the axis. Actually, they repeat in increments of 2 pi. So this gets repeated every 2 pi up and down the frequency axis. What about the phase spectrum? Remember, we had e to the j pi over 2 and e to the minus j pi over 2. So at -1 times our fundamental, we had e to the j pi over 2, which is a phase of pi over 2 radians. And at the positive frequency, we had the minus pi over 2 radians. So that's why you see plus minus pi over 2. And again, those values repeat up and down the frequency axis with a period of 2 pi. So that is a plot of the amplitude and phase spectrum. All right, so that wraps up this example. We went back to using the definition of the DTFS to find the DTFS of a sinusoid. In the next video, we'll go back to our method of inspection and we'll work with a slightly more complicated signal that actually consists of a sum of sines and cosines. Thanks for watching.